Welcome back to Muddy Math, where we take middle school math concepts that are a little muddy and clear them up. Today, it's day 14 of our 28-day journey to finding phi. I am so proud of myself and of you for you all joining in to be a part of this journey. It's not easy to stay committed to something for the whole moon cycle from new moon to new moon, but look at us. From third quarter to third quarter. Last week was the new moon, so this week is the first quarter. And this week we dig in, we get organized, and we really put our work into a focus point and help reorganize all the things we've already learned into our brains, into long-term memory. So you see here that today we want to organize day 14. We want to know these words: pyramid, right triangle, square root, base, height, slant height, Pythagorean theorem, and square. Many of these words you already feel acquainted with, and that's excellent. For those of you out there who have no idea what any of those words are, welcome. You have a lot to learn, and that's something to celebrate. Those of you who already feel like experts about this material, can you find an edge of your understanding and really digging and find a learning point here? I really want to welcome this journey to be something that an entire family can do together, to encourage mathematics as a way to communicate and connect with each other, and less about something being right or wrong. In our session today, we want to understand how can we organize everything we have learned by taking on yet another perspective. Another perspective. Yes, there are an infinite number of possibilities of the way to look at something and to learn something. So I'm constantly pressing myself, how am I going to talk about phi for 28 days? And look at us, we're doing it, okay? And then how can phi be modeled three-dimensionally? So as a quick activator, I'd like you all to take a look at two photos that I captured on a public golf course nearby. I promise that I was way far away from any other people, okay? But what I did is I noticed, I'm like, oh, here's some rates of change. Okay, so what I would love for you to do is to look at this staircase on a golf course, and I want you to describe the rate of change. Now, to give you some scale, okay, if you look at the picture on the right, there's a little golf ball all the way to the right. So that is the scale for you. Now, a golf ball is what? About an inch in diameter, the cross-section of a spherical golf ball. Let's see, the diameter of a golf ball. See, I don't know everything. I'm just Googling it, and it's no big deal. 42 7/10 of a millimeter, which is about 1.68 inches, okay? And I hope that gives you some idea of your scale here. So golf ball is 1.68 inches. So what's the rate of change on this staircase? What is the rate of change on this staircase? What is the rate of change for this staircase? What is the rate of change for this staircase? Rate of change. Well, I'm going to sketch it out. It's a two-dimensional staircase. No, it's not. It's 3 dimensions, and this is our first time really getting to talk about dimensions. So a staircase is 3-dimensional, but this photograph is 2-dimensional. So if you take your hand and you I don't really want to encourage you to touch your computer screen, but find something flat around you. Okay, my whiteboard is flat. This is 2-dimensional. So when I draw a 2-dimensional sketch of a 3-dimensional object, I'm sort of taking a cross-section. I'm just looking at, 2-dimensional slice of something in 3 dimensions. And that's what you see here. So we have these logs. This is just, a staircase built with logs. It's pretty cool, okay? It looks like the stepping part where you put your feet. Hey, here's your golf club and your ball. Okay. Is longer than the rise where you have to lift up your knees, right? So I'm going to say that in this case, it's decreasing from left to right. So from left to right, the staircase is decreasing. Even if this person's going up the stairs, we read from left to right. So this is a decreasing rate of change. Okay, and I'm going to say average rate of change, right? Because we're thinking about on average, if this was a straight line, okay, if that was a straight line going through the staircase, it'd be the average rate of change. It is decreasing, and then remember, if the rate of change is at a 45-degree angle to a horizontal line, it's a rate of change of -1 here. So this, let's see, oh, thanks, Dad, for my new dun-da-da-da giant compass and protractor. Woo, woo, woo. These are great tools to have in your Go Out in Nature toolkit. It has inches, centimeters, and a protractor. Any family member that wants to support your child getting a little discovery toolkit to go out in nature and measure and sketch and learn about math, I really recommend these. They're called Bullseye Compasses, and they are fabulous. Obviously, the one you would get is probably this big, but this is a giant one, which I love too. You could throw this in your giant navigation toolkit. But anyway, so if I look at my compass, if I go straight up, that's 90 degrees, okay? That's 90 degrees. So 45 degrees is half that much, and that is a rate of change of +1 if it's increasing. So this is a +1 rate of change, okay? The horizontal is a 0 rate of change. Vertical is undefined. More on that later. Oh, you guys can't see me. I really appreciate that we are on YouTube Kids, so everyone feels welcome to participate, okay? But I do wish there were comments, because you could be like, Sam, we can't see the board, which is what my students do in class all the time. I'm writing on the projector, and they're like, Miss Flat, I can't see the board. Well, some of you did. Anyway, I missed you all. I'm excited to be back. Okay, so here's 45 degrees coming off the other edge. The left side of the undefined line, and this is a slope of -1. So you guys tell me, is our staircase shallower or steeper than -1? Here's -1. Yes, you're right, it's shallower, okay? So this has a more mellow, a shallower rate of change. So maybe when people are carrying their big golf bags, right, with all their golf clubs sticking out, that it's easier to climb the stairs than if it were super steep, right? A super steep staircase would be rather dangerous for people carrying a bunch of golf clubs, maybe. I don't know. I don't carry golf clubs. But anyway, welcome back. Let's get organized. So what we're going to do today, if you downloaded the PDF enhancement, you'll be able to stay right on track with the lesson. I'm always learning about this process, bringing you content through live streams. So I changed the format of the PDF enhancement a little bit. So if you like this one better, send me an email, muddymath@gmail.com, or if you're one of my students, Flynn_Samantha@mybps.us. And let me know if you like these better or if you preferred the old style. Okay, but here we have our first sort of slide, just giving us our know, understand, do. And we want to understand how can we organize everything we've learned by taking on yet another perspective. And we want to know how we can modify three-dimensionally. So we got a taste of three-dimensional and two-dimensional, thinking about the staircase as a three-dimensional object in real life, but then drawing it two-dimensionally, kind of a cross-section, thinking about a slice of that staircase, and then analyzing it on a two-dimensional plane, coordinate plane, rectangular plane of going, what's the rise over the run? Well, it's going to be less than 1. If it was 1, it would be the same distance, but the height is shallower, so we're going over more than we're going down. Okay, and it's a shallow rate of change. So many ways to think about all of this. Okay. So our first word is pyramid. Now, if you have the PDF enhancement at home, you will have an isometric grid on yours. So cool. So when I did Design Squad Global for PBS Kids, we learned a lot about sketching with isometric grids. So this is a way that we can really start to see 3 dimensions. If you notice, we used to go on a coordinate grid. The past 2 weeks, we were looking at a coordinate plane, which had squares everywhere. And what do we have here? We have, what are they? They're not squares. What are they? I don't want to take away a learning moment for you. Think about where quadrilateral, parallelogram, rhombus. What is it? Well, their opposite sides are parallel. They're kind of like diamonds. They're quadrilaterals. Opposite vertices are congruent. Okay, so anyway, this is an isometric sketching grid, and a lot of designers use this type of grid to sketch their ideas because you can get a 3-dimensional feel for the objects you're drawing. So a pyramid is a 3D solid with a single base and faces that form an apex. Base can be varying polygons. Okay, so let's model pyramids with different shapes, and that's how we're going to kind of get started today. So let's model pyramids with different shapes. And my vision for this, perfect, was to put me sort of in the middle here. There we go. All right. So again, those of you wondering how to bring this idea to young people in your family, I stole all these from my less than 1-year-old daughter. So for those of you that are interested in 3-dimensional math, this is a great opportunity to just start describing, not necessarily naming, objects. We have a sphere. Is this a pyramid? Well, just from that slice, you might say it could be, but it's actually a triangular prism because it doesn't come to an apex. And what do I mean by apex? Well, I think my daughter's pyramid is in the car seat, but this is a cone. This is not a pyramid because it doesn't have a polygon base. It has a circle base. A circle is not a polygon. A square is a polygon. A 3-dimensional square could be a cube. All 6 faces are congruent. This cone, okay, if you're in calculus, if you're in high school joining in with your middle school brother, sister, cousin, okay, what are the conic sections? Cross sections of a cone. That's a very common thing to investigate in high school level math classes. Okay, what are the sections of a sphere? What is this? So it doesn't have a polygon base, so it can't be a pyramid. Can't be a prism because a prism has to have a polygon base. It actually has 2 polygon bases. So if you look back at our triangular prism, okay, this has 2 congruent bases that are triangles. And so if we stacked it on top of each other, then these are the faces. Okay, these are the faces because they're rectangles connecting the 2 bases that are parallel. They're parallel. Okay, this is like an egg shape. This is something we would probably need polar coordinates for, something we talked about. Not an isometric grid, not a coordinate plane, but maybe polar coordinates, I've never been so inspired by polar coordinates before in my entire career. Okay, what is this? It's a rectangle. That's the cross section. It's only what you can see now. What's this? Ooh, I probably gave it away. That's a square, cross section, but when we look at it with a different angle, imagine the isometric grid, okay? So let me flip back to the isometric grid. Okay, you see how the isometric grid can help us sketch the 3-dimensionality of these objects because on an angle, it makes that same little diamond shape, right? But then we can draw these vertical lines coming off of the corners and actually create what looks like something popping in and out of your page. So this is a rectangular prism, okay? And then finally another triangular prism. So we see 2 different types of triangular prisms. But what's a pyramid? Well, I love showing what things are not before I show what they are. So let's take a look at what a pyramid is. What I want you to do is, if you have the PDF enhancement, try drawing any three-dimensional object. Any three-dimensional object. Try it. Give it a try. If you don't, maybe you have Play-Doh. Can you form a three-dimensional object? Or can you just look around your house? Look, a nail file. A rectangular prism nail file. A cylinder. Did I even tell you guys what this was? This is a cylinder. It's like a prism, but it has a circle base, so it's a cylinder. Cylindric? Ooh, cylindric. Cylindric cup or a cylindric tea mug. Check that out. Experiment, fail, learn, repeat. How fitting. And that's a Leniskit symbol, the infinity symbol. Anyway, I am so excited to be here. Can you tell? Please find some 3D solids around you or try to draw them on your paper. If you don't have isometric grid paper, you can just make your own. So if you see, I'm making an isometric grid on the whiteboard using dots, okay? And they all sort of form these diamonds. So if I wanted to try to draw a pyramid, okay, I would connect these dots. So on your enhancement PDF, let me use a darker marker. A darker marker, darker marker. Okay. Okay, that looks like the base of my rectangular prism, but I don't want it to come to another flat base. I want it to come to an apex, like the cone. So instead of drawing completely vertical bars, right, the vertical bars would give me a rectangular prism. Okay? And then you can draw in dotted lines to show the parts that you can't see. But I don't want a prism. Prisms have two bases that are parallel. I want it to come to an apex. I want it to come to a point. So instead of doing vertical bars coming straight up to make a pyramid, I want, and I lost some of my isometric points here. It's okay. Okay, this is going to be the square base of the pyramid, and then this will be my apex. And this is called the capital B base. Okay, capital B base is referring to the three-dimensional object's base. Okay, and then the apex meets the base at a right angle. So the apex comes straight down through the object. Okay, so here I have my cone. That apex would meet the base circle right in the middle there, right in the center of the circle. It meets the base at a right angle. Okay, and then here comes my pyramid. Okay, so that's how we have started class today with pyramids. Okay, it's a 3D solid with a single base and faces that form an apex. The base can be varying polygons. We're going to look at a square pyramid. Okay, so next we have square pyramid, a 3D solid with a square base and faces that form an apex. So if instead, I could have formed a pyramid on the top of this and just bring it to a point, and that becomes my pyramid. I'm going to search the car seat today when the baby gets back and try to find that pyramid for you all tomorrow. But here we go. Going on. We're going to build a square pyramid with a radius 1 and a slant height of 5. So slant height, this is a new word here. And slant height, okay, the height of a pyramid is, if this was the cross section of the pyramid, of this same pyramid, here's the big B base, Okay, here's the apex. The height of the pyramid is the length of the apex to the base, where the apex meets the base at a right angle. So this is the height. And I'm going to zoom in just because, why not, right? Now the slant height, now that height right here is from the apex to the center of the base meeting at a right angle. So that's the height, that's the height. Now the slant height is now this is a cone, it's not a pyramid, but the slant height, where the height goes through the center of the solid, the slant height is this distance that we can actually touch with our fingers. So the slant height is from the apex to the base on the edge of the actual solid. So my slant height, let's see, let's just get my wits about me here if this is going to meet at So the slant height is on the edge of the pyramid. And this right triangle is very special, especially when it comes to us learning about phi, because if we assume that this square has a radius of 1, so I know that squares, you don't typically consider them to have a radius because a radius is related to a circle. But what we're imagining is that there is a circle inscribed in this square with a radius of 1. So we know that the base, little b base, of this right triangle equals 1. Okay? Then what we can see in ancient Egypt is that the Egyptians built the pyramids using phi. Some of the pyramids, I believe the Pyramid of Giza, seems to have been created in the likeness of phi, the golden ratio. Okay, and yesterday when I was preparing for this lesson, I was doing a lot of sketches trying to figure out how to bring this content to you all. And the idea is that if, let's see, let me just erase some of these lines, okay? If the base of the right triangle formed in the pyramid, it's a slice out of the pyramid, is 1, and the height of the pyramid from the apex to the base is the square root of phi, then the slant height of the pyramid is phi. And I found this all on the goldennumber.net. It's a fascinating website all about the golden ratio, where it is in our world, in our lives, and how we can access it and how we can be amazed by it. So if you go to my website, muddymath.com, okay, you'll see that it is linked at the bottom. Okay, I found this guy. He's on Kickstarter trying to get this beautiful, beautiful coloring book made out of objects that live in the golden ratio. The coloring book's like $300 on Amazon. It's crazy. But anyway, golden ratio is in the Great Pyramid of Giza site, topography. Okay, so if you click that link from my website, it'll take you to the goldennumber.net, which is an incredible site, and boom, there you go. That's just what I drew for you all, is this relationship of the pyramids in ancient Egypt. So these are all like floor plans of all the sites in ancient Egypt that they also think are related to the golden ratio. And that's the amazing thing about the golden ratio versus a circle. A circle, you can look at it and you're like, oh, it's a circle, so its circumference is related to the diameter by pi. But with the golden ratio, you really have to dig deeper and you have to say, where is it? I have to search for it. Does that look like it? How can we measure it? Should we measure in 1 dimension, 2 dimensions, 3 dimensions? It goes on and on, okay? So this was a taste of us trying to get organized. Now, you might be saying, wow, I don't feel any more organized than I did before. But let me show you that I feel more organized because I took time, okay, to organize my thoughts on my whiteboard. Now, wherever you're keeping notes, I feel so lucky that I'm able to have these materials. Okay. Sunday, you guys saw me working on my painting, my FI painting, my project. Ooh, be seen. I hope you were seen, right? Art is whatever you make it, and this is well on its way to be maybe one of my favorite paintings. But yesterday, I was trying to get organized with a lot of thoughts for you all. So my organization and your organization are very different, but I'm just feeding you more ways of looking at a single concept and accessing different math tools around you. So it could be sorting shapes for my kindergartners. It could be rate of change for my middle schoolers. It could be investigating the Pythagorean theorem a little bit more for what we're doing this week in terms of pyramids. It could be conic sections if you're in high school or college and applying conic sections to a sphere. What do you imagine would happen there? So I'm just encouraging you. I'm just here to peel back any anxieties that you have ever had or been kind of burdened with in life about math. Apparently, Joe Buller did some surveys. About 50% of the humans walking out there on Earth are fearful of math. And this is not fearful. This is so cool, a way to communicate, a way to plug in with others, a way to plug in with yourself and your true interests, okay? We know from the book The Nature Fix that nature reduces our anxiety levels, especially fractal patterns like trees and pine cones, okay? If you can get by the water, that helps too. So why not marry nature with mathematics? Something that for half of you, this is causing stress for, and for half of you, it's not. But regardless, let's bring down our stress levels. Let's not pump out cortisol into our bodies when we think about math, the stress hormone. Let's stay calm. Let's investigate math, and let's be proud of what we're doing. So your homework, whatever, it's not homework. That might cause you anxiety. No, it's not homework. Your challenge, your invitation, let's say invitation. I invite you all to get organized and to play with pyramids. So that's all we're doing. That's all we had time for today. I will extend the slides from today and the PDF enhancement to tomorrow, day 15. But we will continue looking at these. Okay, we have the right triangle to investigate. So can you explore right triangles? Yes, you can. Yes, you can. Might you have some frustration and struggle? Yes, you might. Is that a time to learn? Yes, it is. Do we celebrate times to learn? Yes, we do. Okay, so we're going to look at the right triangle in more detail, especially related to phi and the amazing Egyptians that brought that to us. The Pythagorean theorem, I've talked about this a little bit before. Okay, we want to look at the Pythagorean theorem and see how that relates to the pyramids in ancient Egypt. Square root, in order to really understand the Pythagorean theorem and this relationship between right triangles, we need to understand what a square root is a little bit more. Base height, slant height, we did this. Check it off, we did this, but we can still improve more. So all of this is in the PDF enhancement. Please leave me a comment on muddymath.com, day 14, organize, on how I can help you get organized. We are all different humans walking on this earth with different ways of organization. So you let me know what you want to do, and I can help tailor fit that to you. Organizing might be going out and organizing shapes into piles. Say, okay, little brother, go get 5 pine cones. Now go get 6. Or college sister, find all the conic sections in the house, right? Get organized. And smile. You did it. Day 14, I'm so proud of you. Sam here, signing off. Stay tuned this week for the live streams. Please share this journey with others. The more community we can build, especially in this time of being physically apart from others, is so important. And what better way to use your time than to redefine your relationship with math as a powerful tool that you, by your human rights, have a right to fully understand and communicate with. So I hope my passion is contagious. I love this. I love you all. See you tomorrow. Be well.